Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Fine. So I don't think you'll see anything here that disagrees with the previous presentation, and probably a lot which overlaps. Because I certainly have several slides where I stress the fact that we don't know what we're talking about at this stage. So, and you notice this is called data analytics because at least in some documents that's a powerful word which summons up sort of great activity. And so, and another word, and it's a very broad range as we just heard, so I think it's pretty important actually to clarify what that range is and design courses that tackle those ranges and make offerings which cover that range. Now my personal interest is what I call X-informatics, and I define X-informatics as the applications that are enabled by data science. And if you go to the web, because the web knows everything, does it not, you will find that various informatics areas are defined, such as medical informatics, bioinformatics, cheminformatics, health informatics. I came at the higher today, there was a huge pathology informatics meeting, and Tony Hay and Anne Trethetten taught me that according to a Microsoft survey, there are 70 petabytes of pathology data produced every year. That's medical imagery. And so it's actually the largest field in the world. And they're meeting just, so it's all going on around us, so that's pretty interesting. Anyway, but what's interesting, it's actually called pathology informatics. There's astroinformatics that have been set up, social informatics, business informatics, security informatics, intelligence informatics. Now, I invented a field, because I didn't know what else to call it, which I called lifestyle informatics, which was basically covers all the ideas that, say, Facebook and Bing and Google and Twitter and things use to make our life wonderful, namely all these Web 2.0 commodity world we live in, smartphones and things like that. So I didn't see a nice name for that, so I called it lifestyle informatics. More humdrumly, I invented also radar informatics that describes some recent work I was doing, because radar also produces lots of images which have to be analyzed, and indeed it's actually the same algorithms as pathology informatics. They're very similar algorithms. It's sort of interesting to note that an area that doesn't exist is physics informatics. Even though it's quite obvious it should exist because discovery of the Higgs boson requires lots and lots of physics graduate students writing lots and lots of software to do data analysis.
So Jeffrey, I tend to agree with this approach, but I find people who are clearly doing what I would call, say, astroinformatics, who absolutely do not self-identify as
of course.
people, they're astronomers. Right? So where does the line fall between radar data analysis or radar, whatever the data set?
Well, that's presumably why we're here. The field of data science is growing. One way we can help it grow is to note, well, let me go to physics informatics. The discovery of the Higgs was enabled by the huge effort to produce the open science grid and all the analysis and software, and that's all roughly data science, most of it. But it has never been articulated as data science. The poor physics graduate students, remember, some of which I actually had, because I analyzed Fermilab data for many years, so I'm pretty familiar with that field. Those students often go and get software engineering jobs for which actually a data science degree is probably more appropriate. So I think that what your observation points out, that one of the things we ought to be trying to do is to actually identify the informatics components of different fields more precisely. The generalized medical field has done it very well, as we see from the fact that the first 5 of those names are all from the generalized medical field. So and that's extremely common. You write proposals, you're meant to have informatics components in your proposal, and people get informatics degrees. So I think that's a pretty important point. But here I just want to point out I'm making an even simpler statement. There is a set of activities which I call X-informatics, which is using applying data science to lots of different fields, including the ones mentioned here. And I say I invented lifestyle informatics because I didn't see any, because this is the largest use of IT in the world, is to support the Web 2.0, and it doesn't actually have a name as far as I can see. Sometimes there is network science, but that tends to focus on somewhat other issues. It tends to do more on network structure and things like that, rather than the actual analysis of the data from Twitter and things like that, which is, of course, an important part of a lot of that research. But it doesn't have a generalized name. Well, that's possibly part of web science. I agree. Web science and network science are, but I don't think web science, I included supporting smartphones in lifestyle informatics, because our life, at least our students' lives, are built around smartphones and cloud supporting those smartphones, are they not? So anyway, there's too many people on Skype. So let me think, all right, what I want to. All right, so the next point I wanted to make is that at least some of us might remember the field called computational science. And it would be useful to try to understand some lessons we might learn from computational science, which was many years ago I was trying to persuade Caltech to do computational science. Somewhat unsuccessfully, in fact, but I tried to do it. They got me to rename it as physical computation. But if you looked at that field, which was roughly the field that lies between simulation and science, it had various issues which are pretty important in data science. Namely, what type of degree do you offer? And you can have real degrees like masters and PhDs, with the word data science in their name. You can have certificates, minors, you can have tracks. Also, there are various ways you can implement these things as degrees, and also there's also a lot of choices as to how you label the faculty. You can have professors of data science, or you can have a program in data science linking together professors in computer science with professors in physics or something. The program approach has tended to be the most successful. It's more flexible. So I once wrote a paper which noted if you have n fields, you have probably 2 to the n minus 1 possible interdisciplinary fields, and therefore it is not really realistic to establish all possible interdisciplinary fields. And so it's probably better to start with a few core fields and start joining together dynamically in programs. So here's this a little more detailed on computational science. I think there is little doubt that computational science, like data science, is hugely successful as a research area. Things like in the US Exceed and the exascale initiatives, they're all, if you like, driven by computational science. From early universe through fusion, etc. There have been many academic programs, some of which I was associated with, but and that's sometimes called scientific computing, but I would perceive them as less successful as the research activity. The research activity, I think, is unreservedly successful. The academic programs have reservations, and at least 2 reasons which we can, there's one important reason for data science, that is nobody ever agreed what the field was. And also, people did not, I say, appoint faculty in computational science. UC Davis did for a little while, but abandoned it. That's a rather recent episode in that area. The only thing you're guaranteed if you get a degree in computational science is a job with DOE. They will, if you're reasonable, they definitely, DOE loves computational science, but not so many other places. And the other important feature, which is not true for data science, is the field is small. I think the number of, these numbers measured in millions of jobs in data science coming up in the US, that number for people doing supercomputing and parallel computing is not measured in millions. It might be measured in hundreds, something like that. So that's an important difference which needs to be borne in mind when talking to your administrators, that this field is driven by large numbers of jobs. As a counterexample to that, I noticed chemistry, where the field of computational chemistry is very successful. Notice it's a branch of chemistry. It is not a branch of an IT unit. And cheminformatics is actually a branch of IT, and it's got far fewer people in it. That, I believe, is the exception. It is about the only exception I know where the data side is less than the simulation side. There are only about, we happen to do cheminformatics at IU pretty successfully, but we're one of half a dozen places in the US that has cheminformatics. Whereas lots and lots of universities have computational chemistry. UK has some Sheffield is very strong in cheminformatics. And so is Cambridge. Peter Murray Rust is, of course, very strong in that area. But this is an exception. Here's a few more remarks. We've already agreed it's an immature, exciting field. Here's another list of possible terms: data analysis, data mining, data analytics, machine learning, data science, of course, and subfields like information visualization. There is no agreement. So when I analyzed data from Fermilab, I always said I was doing data analysis. I never said I was doing data analytics or data mining. I was data analysis. And the area I was actually always in was called phenomenology, because I did modeling. In order to do that data analysis, I had to write lots of models. And we've already had this on the last talk. We have to look at not only the core issues, but things like security, provenance, metadata, curation, data management. Those are all parts of this field. At IU, we have these interesting conflicts or discussions because some fields like social informatics are being revolutionized, because originally social informatics was dominated by ethnography, interviews and things like that. And now there are at least some scientists in the field who will take billions of cell phone records and do the big data analysis in those areas. So there are some areas which are moving from 20 observations to billions of observations, producing some stress on the system and some disagreement as to the right faculty member to appoint. You can guess which side I would be on, but I'm not in social informatics, so I don't make the decisions. And of course, we have lots of tools. I already pointed out 70 petabytes of pathology. Obviously, there are lots of exciting areas in network science. Obviously, there's some of the data is in metric space, some isn't. And there's some Large Hadron Collider, the type of work I used to do, except it was at Fermilab, not LHC. The dominant final stage is histogramming. It's actually some of the world's simplest data analysis, but it's done at a scale which makes it quite challenging. I like to point out the analogies between earthquakes and the stock market, in that both are time series, both have no fundamental theory. Probably the stock market is more fundamental than earthquakes, because at least you can look at the quality of the company and the brilliance of the people in the company. Whereas in earthquakes, you have no idea essentially what the nature of the faults are. And so, but both of those are probably as much as anything done by what we call pattern informatics, the use of looking at previous events and saying, when you got this squiggle, it produced this event. So that's, and there's been some pretty interesting work along those lines in both those fields. And tweets are also, of course, time series, which you can do this for. I already pointed out the radar and pathologic informatics are the same thing, etc. So here's some stuff which I won't waste your spend time on. But we did write down a list of all the data science degrees. This was done by my colleague Howard Rosenbaum at Indiana University in planning for what we were trying to do. And so you can see a suite of, which probably isn't everything, you can probably add some more, but this is what we found at various universities, and it can be covered in 3 pages. So that's not so many. We do have Syracuse there. So now let me come and make a few remarks about what we're doing at Indiana University, which at least Dennis will know most of this. Except there is some amusing news there. We have a School of Informatics and Computing, and we basically we are merging with the School of Library and Information Science. So the School of Informatics, and we would like to merge with the Department of Statistics, but we're not allowed to do that yet. Anyway, and actually I think statistics ought to be in this. And if you look at this galaxy of capabilities, statistics ought to be there, because it is actually represented by faculty we have, but they're just not in the statistics department. Anyway, so we have these 3 programs now. It is important, you know, as I say, I like informatics, and I stress that I like X-informatics. It's worth noticing that at IU, we have 3 times as many informatics undergraduates as computer science undergraduates. And they're a dominant fiscal force in the school, because we get a lot of tuition money from those students. Some of the, as Dennis probably also knows, some of the senior CS faculty do not think very much of informatics as being a soft science. However, if you look at the employers, well, computer scientists get $2,000 more when they're hard. So that's not a huge difference. And actually, I gave you the mean. The medians are both 55K for both those. So if I could have made them equal. If you want to know how much you gain from getting your master's, it's 14K a year. Of course, your undergraduates have probably got up in their salary to catch up, which is why our master's programs don't have so many American citizens. And if you ask what these people do, which is, because sort of informatics undergraduate is a sort of at least related to data science. Well, it's not so easy there. I have a list of job titles, but there are 125 different employers of last year. So we have about 3 times as many of that students graduating. It's not terribly relevant here. At the graduate level, computer science is twice as big as informatics. It's just it's 3 times smaller at the undergraduate level and twice as big at the graduate level. And here's an interesting piece of politics, which probably also Dennis knows, namely, we are restructuring for the 3rd time. And originally, informatics had all these things here: security, bio, chem, health, music, complex systems, HCI, and social. 3 of those units are moving to computer science, and that's partly the faculty decision, but there's also a decision based on the rating methodology used by the world. Namely, informatics is not rated. Well, this is actually important for data science, and it's setting up new degrees. The rating is done as computer science, and so we had a lot of our strongest faculty were actually in informatics. Now those have actually moved to computer science, so it won't change our rating overnight, but at least we'll change the raw data for our rating. And so the currently computer science faculty is about 50% larger than the informatics faculty. And the 2 dominant parts of informatics faculty left are, well, we could call this lifestyle informatics, complex networks and systems, and HCI. And smaller efforts in chem informatics, health informatics, which will grow, and social informatics. But anyway, this sort of politics illustrates this pretty important issue about how you name things and things like that. It's not trivial. So here's your list of job titles and there are lots of job titles, and they cover the spectrum of where we have business intelligence and everything.
This was from data. This is from
Just the last year. These are the job titles of IU undergraduates. No, I don't think so. No. Data analytics consultant. Here we are. We finished. A lot of them are in this area called UX, user experience. That's a very popular area. That's where a lot of our HCI graduates go. That's not something I have to go to. Anyway, so there you are. So that tells you something. And this also tells you something else. This is the informatics program at the undergraduate level has various cognates, applications. These are the values of X. Well, so they're not all applications like computer science as a cognate, but that tells you what they have. The dominant cognate chosen by the undergraduates is business. Business informatics. The combination of business plus informatics is the favorite undergraduate program. We have no faculty in informatics who study business. Probably we should. That's probably a good area to expand into. So we are proposing to add a master's in data science, and we divided the areas of the courses into 4: data lifecycle, analysis, management, applications. And it is meant to be a beautiful example of the three components of the school working together. Namely, it has computer science, informatics, and library and information science. By the way, another amusing piece of interesting statement, the library and information science school is relabeled as information and library science after this move, because information science is probably the most exciting area. And we will presumably have minors and certificates, and we are currently debating exactly what's to be required and how many courses of each type we will debate. And we do not have a statement on that. And this is what I'm doing. Let me just, this is not quite what I'm doing. So this is another comment. So Indiana University, like most universities, is terrified by online education because they've read about all these distinguished universities like Harvard and MIT and Stanford pouring lots of effort into online education. And obviously there might be a problem because presumably those professors are better than those at Indiana University, and so there's some chance that they will take over. So there's a problem. So anyway, so this is being studied at great some intensity, and there are these 2 startups which are very well known, Udacity and Coursera. And MOOCs have been offered up to 100,000 participants. But I don't see anything wrong with a MOOC with 50 participants, because they're basically the same concept. It is that it's basically reasonably classical online education delivered with rather efficient technology and just generally well done. And I consider it's worth studying for data science for a simple observation. Namely, data science is a new field. Very few universities have courses in this area. Therefore, to have a reservoir, a repository of MOOC-like courses strikes me as a good idea, which will, if we do it right, might actually avoid the mistakes that computational science made, because we'll have some commonality, etc. So I think an international effort to set up MOOCs in data science is worth considering. And I think trying to get some agreement as to what interesting curricula might be would be good to get these MOOCs to cover that. Unfortunately, I do not know of a Microsoft offering for a MOOC tool, but you ought to have one, in my opinion. It's probably more useful than conference management. Yeah. Anyway, there is if you look up MOOC tools, you'll find Drupal has one, but it only has one committer. I'm not certain it's real. Google has one called Course Builder, which was announced 3 weeks ago. And I like it for a simple reason. It's basically a lightweight learning management system. And Dennis also knows this, that Sakai is a heavyweight learning management system. And I do not like heavyweight learning management systems. Whether Course Builder is good enough is not at all obvious. As far as I know, it has never been used significantly. But at least it's got a good start. It's open source. And it's at least roughly right. And one way of doing MOOCs is pretty simple. I call it collecting together with various narrative, pre-recorded talking heads over PowerPoint. And you have your PowerPoint, you have your lecturer speaking, and you record on video the PowerPoint, where PowerPoint can also be desktop, obviously web pages and things, course material, and the person talking. So that's the classic, simple way of doing that. You make 10, 20-minute segments like that and link them together. So this is my, what if it will, yes, sorry. Yes, so I'm going to try to use a MOOC for this course I'm teaching next semester, which actually was the course I first taught when I came to Indiana University, but I was told by a distinguished professor it was a bad idea, which was called Informatics. And so I'm revisiting that, because I think Informatics is a pretty reasonable idea, and I would view this as a candidate for a very, very broad overview of data science and its application. And I will build it as I did last time around this pipeline, from observation through the various steps up through discovery, which you can call knowledge discovery, scientific discovery, or wisdom. And I will go through lots of examples. Each of those examples is a nice thing for the MOOC, because you can just make separate modules on each example. And then I'll try to describe these various things which we need. I mean, essentially all the components we just said. If I haven't quite decided whether I need lab sessions. If I do, they'll be built using R and appliances, so they can be run on virtual machines. I think if you're going to do MOOCs, you better have it virtualized so people can run it on some downloaded virtual machine if there's not enough space on the servers. So I'm working on that course at the moment, which I will offer next semester. This is an informatics undergraduate course, senior, advanced undergraduate course. So that's a good time to stop. So I think this is a pretty exciting area, and like most exciting areas, it's pretty confused. But there are lots of things that can be done, but I do think this field should avoid the fate of computational science, and it stands a better chance of success. But it does need, I think, to try to get some international agreement on not the curricula, as the previous speaker said, aspects of curricula that could be very valuable.
Thank you, Jeffrey. That was fantastic.